All right. Advance. Okay, talk's loading. Oh, wait, where do I point it to? Down here? Where's the receiver? Okay, but okay. There we go. Okay, we're loading. AWE 2024. By the way, Tony Parisi's a friend. He's a great, great advocate for Web3. Warning, this talk is not about Web3. I used to be in Web3. But it's about how in 84 slides, we're going to push the needle of XR, the industry of XR, forward. So June 18th, that's today's date. Here's a talk overview. This talk is incredibly dense. So the first half of the talk will be a single percentage technical. I don't know where everyone comes from. All I know is that it's going to be technical. Maybe you're already an advanced machine learning engineer from FAIR or Berkeley's AI lab. I don't know. Midway, we'll have that's the catch-up portion. We'll have a brief emoji break. And then we'll have a making it simple as possible. We'll also call that the application MySAP. So making it simple as possible is the acronym MySAP. Here's some background on myself. And then we dive straight into liquid neural nets. So it was already kind of covered. This is the complex version. We're going to skip all of that because there's no time for any of it. Here's the basic version. So for almost 10 years, I began in the software side of things, and then I also switched out into hardware. So at this point, almost, I guess, 8.5 years into it, we're amongst the best in the nation at smart glasses. But also, on the other end of the spectrum is neuroscience, which is actually where liquid neural nets starts. So liquid neural nets are a research project that came out of MIT's CSAIL lab with Ramin Hazani, who I'll reference heavily in this talk. There's a really important edge to liquid neural nets that haven't quite broken into any sort of application here, so this will be the smallest portion of the presentation. So you have to keep in mind what we're looking for here is what neural nets used to do and what liquid neural nets are meant to solve. And so one of those three parts of that is the great, great generation, like my vision's a little off, sorry, and the entire left side. So this is a convolutional neural net, and you can see that massive chunk. It looks like a GitHub commit history log. Those are the different layers of what a convolutional neural net does to solve like a self-driving task, and also any sort of prediction behavior agents and whatnot. So what liquid neural nets do is they actually cut that down, and you can see there's actually only 19 in that column. So what is it that liquid neural nets do differently that allows them to just drop all of those multi-layer perceptrons and deep layerings to the neural net? They actually rely heavily on, on the causality aspect of this slide. So it was on the previous one, actually, so let me go back. I see there's one duplicate slide. Okay, so the neural circuit policy is actually the core attribute of what makes a liquid neural net like sophisticated enough to basically biomimic exactly what the human mind is capable of generating. But then that's why it's able to go comb through those patterns over and over again without such as a recurrent neural network, which is acts in linear sequence. There's one other aspect to this. So here are the applications, and my vision's really off, but the the true benefits are basically in that light green box down there. I might be able to read it actually off of here. So it's the scalability and the fact that it's able to, so like the furthest right hand column is like what us as humans who are not researchers will see. The middle portion is the uses, what we found from like applications of liquid neural nets. They're able to cause more memory. They're able to generate better, but that's like kind of caveated by the next architecture that we'll evaluate. And then lastly, they just have very great variety. verifiability and robustness. Okay, so here's where solid-state models come in. Solid-state models are not straightforward. So anyone who's able to see this for like the first time will have a lot of confusion reading it. It's because solid-state models themselves actually massively overlap with proficient architectures when the solid-state models themselves are meant to be more efficient. So solid-state models actually do rely on the attention mechanism of transformers, which is the next slide. But they also can have this duality where they also are in and out of structured sequence space, essentially. So I'll get into it. So here's where we're at in 2024, but this is from 2017. So this is the Ilya. I mean, there's many authors to the paper, but one of them is actually a Web3 founder of Near Protocol. His name's Ilya, and so what it is there's encoder layers and decoder layers, and that's the transformer, that's the T in GPT, so pre-trained transformer. And so then you can see the multi-layer perceptron, the attention layer heads, and then the KV cache, which will be important, but also keep in mind this is the dense portion of the talk, so you won't need to know it by the end. Okay, so the furthest left is where we were in like 2013 to 2016, and that was a convolutional neural net that was wrapped in a normalization layer, and then used, like for example, ResNet is over many different images, and based on how many convolutions it goes through, it gets a sharper distinction or resolution of what it semantically wants to represent. Transformers we just went over, it's a attention network. And then finally, the state space neural net is where examples of models such as Mamba come in, and then this is the innovation in which you're actually able to run these models on edge compute. So we're going to focus on this. And here's Mamba's architecture a little bit more laid out, and you can see at the bottom there that the middle section is the same layer of the sequence transformation layer. And all that's meant to say is that these were, in progression, different ways of sequencing data to basically run machine learning workloads over. And I had to put this in. It's part of the paper. I'm not the best at explaining it. So I'm doing my due diligence by putting it in, but expanded, this is like a core principle similar to how transformers, attention heads, and the different solutions they do to tokenize. Oops, I hope I didn't skip it. Okay, so yeah, the recurrent neural net. So here's basically what the problem is. So they have natural autoregressive model, and so all that means is that it combs through the data in like a linear and normal fashion. However, it's slow on accelerators and like poor optimization, which we saw, and that's why like ResNet isn't SOTA state of the art in 2024. And so then attention transformers, they have strong performance and they're great. They're fantastic at being parallelized. Sorry, at parallelizability. Parallelability. Okay. Anyways, so the only problem is that's quadratic time in that like the linear time inference is like these are two faults that if you comb over the data with its token execution, then you're actually wasting a ton of compute and it's not as efficient as it could possibly be. And lastly, we have selective state space models. And so the efficiency comes with both parallelizability and then also basically some of the fastest inference we'll see in a second, the different benchmarks they're able to see in comparison to Gemini, Mistral, and various models that are state SOTA. Yeah, let's skip that. Okay, so it's also called structured state space models. So if you ever see S4, it's basically the same thing. What's really important here is that you can see that there's a continuous regression, representation, and then you can see like basically each one is from so the state space models are the first one, the recurrent middle are the middle, and then the convolutional. And you're able to see like where the operator sits on what signals are important and then how to comb through those sequences. That's the most important aspect of this slide. And same with the efficient auto regressivity of compute. And then lastly, same thing with how parallelizable it is. Okay, so we're almost off of state space models. And so what's key about this is the trade-offs of sequence models. They can be understood through like examining the autoregressive state. So all that means is that we're able to take some of the best of the recurrent neural nets and then make sure that we strip out anything else that isn't mission critical other than using the same attention heads and then also some of the ODE's differential equation ordinal. Okay, and I think we're going to cut out some of this. It just gets denser and denser. This is the cache. This is actually really important, actually. So the state of cache is also really important. Cache is the memory. This is based on compression versus no compression. I just realized there's like 16 slides of the same thing, and there's a little bit less of each one other one. Anyway, so we have to keep in mind that a compression is a key aspect of a state space model. So something that has compression is more efficient, but is less performant, and then vice versa for something that has less compression. However, there's no free lunch. Like, we can't have both of these. So one of the solutions is Mamba has come out with Mamba 2 as of actually 48 hours ago, maybe even 72 at this point. And we're seeing the old benchmarks from Mamba's initial, Mamba's initial run against other models, and the bold is obviously Mamba, and how it's scoring in the different, so that's 2 billion parameter model, 70 million parameter model, and lastly, we get off state space models. Oh yeah, and so you can tell that it's really important for these models that are linear scaling rather than quadratic, because then they comb over the data, they're autoregressive, and then hardware is something we're going to get back to in just a short second, because actually one of my slides is just straight up notes on this. I thought it was just cool to discuss. Okay, finally, for state space models, Paul Allen's institute, so Jamba has been released in March 31st of this year, and it looks like this. It's a mixture of experts, so it's a combination of the best of sampling from different LLM architectures, as well as you'll notice that there's some attention from attention is all you need, the transformer layer. So they're not completely decoupled. This is why it's confusing. That first graphic is important, because you'll see how there was an overlaying square over square over square, because some of the most efficient executions are still making use of the transformer architecture and the attention, or the token execution. Okay, so lastly, this guy's really cool. I met him this year, as well as another teammate of his. And so Cartesia is creating its own model against Jamba, and Cartesia basically has some of the best researchers out of Stanford who are also cited in these slides. And they're actually who are targeting Samsung and Qualcomm for edge compute, which is really interesting. So they're trying to get their models to run on those devices as opposed to compete against larger hyperscalers. Okay, so here's the hardware. Sorry, this stuff gets like just so dense. Okay, so I'm circled flash attention because it's important to know that there's like different solutions, but they're on different sides of like how the model is run. So there's DSPy, and DSPy is a programmatic solution to how people have normally done large language models. This is relatively recent out of Stanford. But most importantly, there's VLM, and VLM is really important to note because it's the flash attention that comes from like the researcher Tree Dao, who also published the state space model papers. It's like it optimizes for like the attention operation as opposed to like the VLM is more focused on memory access, and we'll see KV caching in a second. So what's really cool is coming out of Berkeley, and obviously they get actually first, because I know them personally, they get first class access to AMD's models, the MI300. I got to go look a little bit quicker, so we're going to speed through some of these slides. And so this is the page detention that came out of VLM last year. It's complex, but here's the important part. So the important part is that it reduces memory fragmentation, and then it also reduces memory usage when sharing. So like all this means is that you could couple together a bunch of different systems and have efficiency all around. Okay, so here's the architecture for VLM, and you'll notice that Ray is one of the options for deployment, and they do distributed training. So Ray is also well known for their A16Z backed, and they are original inference training for OpenAI, actually. Let's see. I got to go a little bit quicker. OK, so here's where they are today. It's just a whole slew of like different optimizations. I'd actually really point out the better quantization support. That's really important as things get down to like different floating points in like 1-bit LLMs, which is incredible. I think it's just theoretical. Or also infinite context windows, which infinite context from Google. OK, and let's see. Oh yeah, here's where the links are to VLM. And we're going to hook this real quick into hardware. And so hardware, you'll notice that they actually use VLM. And so this is the MI300X from earlier when I mentioned it. And it's really cool how like well supported like the industry is willing to embrace such an open source project that just came out of Berkeley's their Sky Compute Lab. OK, so thus one way of looking at this is that the same memory capacity that was released for Blackwell's, so that's the chip that Jensen had up on stage, the 192 GB. It's actually the same for both AMD's SOTA, state-of-the-art, and NVIDIA, but NVIDIA is actually able to process the memory 2.8 terabytes per second faster. And then, sorry, these are just notes because I really didn't know how to fit this in without kind of just getting really nerdy. And so what's really important in this chunk of text is just that, so the CPU, the bidirectionalness of the Grace Hopper, or sorry, the GH200, the CPU actually can't keep up with how fast NVIDIA's GPU progress has been. So right now it's only able to, while it can do 900 gigabytes per second read-write, it only really can do unless it's opened by the private API from NVIDIA, it actually is really slow. I got to go much faster. Sorry. OK, so that top chunk, this is the important part of what these new architectures bring to VLM. And lastly, finally, everyone's waiting for applications. All right, so real quick, we can take the transformer architecture that we see with attention is all we need from 2017, and you're actually able to swap out different elements, different components of it. So it turns out that execution of the tokenization, it can just be swapped out for trajectories and even waypoint planning. So you can do motion optimization through quantization, which is really cool. And so this is the emoji break, because now we're going to strip all this away and make it make sense. OK, so the architecture that's taken from transformers ends up being pretty cross-applicable to most mediums. It's a little bit harder for continuous versus discontinuous to be like text on that end of spectrum. Continuous would be like video and audio and motion. But it's really interesting how even that aspect of things doesn't disrupt something like Waymo and Zoox from creating new motion planning architectures and executions. All right, and I think we're getting to the best part, and we've got 3 minutes for questions. So for spatial computing, why don't we create a different model for all of this? Why don't we do speed and generation of time? So what it's meant by that, oops, let me go back. I'll get to that. What I mean by that is we have all these tools. We have all the huge archive of machine learning papers, but nobody's actually addressing anything that spatial computing does best, which is what z-axis compute. That's the definition of spatial computing. And so we've worked on it for a long time. So the whole point of this meme was what is the Uber of spatial computing? Who is that? How is it done? How's it executed? What's the rollout look like? And how do you fend off? So I guess we'll never know, maybe in the near future. But the very last aspect of this, couldn't figure out where I could put any of this stuff in. So there's a couple updates on our blog, which I'll link at the very end. We're publishing a spatial computing Bible where we'll address that last new machine learning model. And then the other aspect of this is we're also going to include different backprop engine selections in different So a success algorithm, which is basically a second order derivation of like, oh, well, how once we have this speed to generation of time, like what do we do with that? And so you probably would want to write success algorithms. The little last quote right there, top 4 is really important. I really think that at the end of the day, we're going to have a phone, a laptop, a neural interface, and a glass. And 50% of that is already owned by Apple. So if there's any like spatial, if there's any Web3 like digital autonomy sense in this whole presentation, is that like why don't we do something about like the like latter half of that mountain where like maybe it's not all verticalized into one company that rules you. All right, and so feel free to contact me. My actual handle on Discord is spatial computing. Yeah, literally at spatial computing on Discord, and then reality metadata for Twitter. Thank you, and questions for 2 minutes. Thank you.
All right, time for one question. Anyone else besides Lex? Okay.
Oh yeah, and you get a gift card if you ask a question.
It's an absolute honor. This is great, man. What
Yeah,
a great combination of academic with real world, current, and very real. Always, there's definitely the question that you mentioned of what autonomy and safety,
Yes.
AI. The biggest kind of talk of the topic is like how much should be put into safety, how
Yes.
much like the resources, safety versus growth, right?
Yeah.
But tell us your thoughts and how could we participate? I think you're like of this community. You're really pushing the boundaries here. If we want to be part of the Bible, or tell us, like, how do we be part of it? What
Right. Yeah. Look, I think it's really important that we try to implement, this homeomorphic encryption and this homomorphic encryption. Homomorphic encryption would just basically be shielding processes run on the device. That's like a fantastic way to save privacy. Apple hasn't implemented it. There's only like 1 or 2 apps on the App Store that have that. Actually, I didn't get to mention it at any point, but it's a D-line. There's an event each year, and we just pay for people to come. Like it's kind of silly, but we're on the 4th year of it, and you just fill out a form, and then you tell us how expensive all your stuff is, and we pay for it. And one of the really cool journeys this is taking me down is I actually met Sam Altman through doing all of this really crazy stuff. And Sam Altman doesn't really understand spatial computing very well. So we're really hoping to have advocates basically come and make OpenAI more open, but most importantly, just get it to be like up to speed with Z-axis compute. All right. Thank you. Absolutely.
Awesome. All right, let's give a hand for Dev Kennedy. Thanks very much.